This example comes out of section 1.1, linear functions and the tangent problem. In this example, we're asked specifically to find the equation of the tangent line to the parabola y equals x squared at the point 3, 9. This is kind of our first venture into what we would actually call calculus. Calculus, one of the problems we run into is how to find the slope of a tangent line. First of all, we need to know what a tangent line is. If you have a curve of some kind, whether that curve be a circle, or a parabola, or some other polynomial of some kind, a tangent line comes and touches that curve just in one particular spot. So whatever point they are interested in, we can find tangent lines at any kind of spot like this. So those are all called tangent lines. There's a nice description and picture of those kind of on page 7 of your book that defines, a tangent line is something that just touches. A secant line, on the other hand, is something that goes through 2 points on that curve. So, for example, of a circle, I could pick 2 points and say, okay, there's a secant line there. If I had a parabola, again, I could pick some 2 points on this parabola and connect them. And if I had some polynomial-looking thing, I could connect 2 dots on there, and these are called secant lines. The thing that makes secant lines right now easier to determine for us than tangent lines is that all we've ever really learned about slope is that it's rise over run, that we use 2 points and we find the slope of a line that way by saying, the change in y over the change in x. That slope equals delta y over delta x, or in other words, y2 minus y1 over x2 minus x1, which in the case of a secant line, you have 2 points. You just find the rise over run between 2 points. The tangent line problem is kind of one of the roots of calculus, especially our beginning part of calculus, is to try to figure this out. So this question specifically talks about the parabola y equals x squared. Hopefully you're fairly familiar with that parabola from your previous courses. Y equals x squared looks like this. They're talking about a point at 1, 2, 3, 9, so let's put that point right there. And we want to call that point P 3, 9. We can't yet, we don't have the skills or the tools to just straight find the tangent line slope there. But what we can do is kind of artificially say, well, let's make a point Q. Any point Q on this parabola is going to have the point x, y, and even more specifically than that, xy could be written as x, x squared, since y equals x squared for this particular graph. So if slope equals rise over run, it's going to be y minus 9 over x minus 3. Or, again, for this one, x squared minus 9 over x minus 3 is the slope from any point Q to the point P that we're talking about. So if we pick a point Q that's really close to P, like for example, let's let Q be pretty close, let's say 4, 16. That's relatively close. So what's the slope of the secant line when we're talking from P to Q in that case? Well, it's going to be the change in y coordinates. So 16 minus 9 divided by 4 minus 3, and you get a slope of 7. Now, that's fine. That is not the slope of our tangent line, but it gives us a rough estimate. But we could try something even closer. So we could take, for example, a number like, let's let Q be when x is 3.1. Or we could let Q be when x is 2.9. Take numbers that are very, very close to 3 and get a sense of what does this slope look like as Q gets really, really, really close to P. So we'll do that for 3.1, 2.9, let Q be 3.001, make it ridiculously close, let Q be 2.999. So I'll grab a calculator. So doing these calculations quickly without showing every single detail, if I pick a point Q of 3.1, find the other coordinate find the slope from that one to point P, I get a slope of 6.1. If I go just to the left side instead, I get 5.9. If I go really, really close, I get 6.001. And if I go really close on the other side, I get 5.999. So it's not a hard thing to imagine that the slope of the tangent line appears to be 6. And we will have a more concrete method of doing that later on. But for now, since we don't know about limits, we don't know about derivatives, this is what we're going to do. We're going to estimate it, and in this case it's a pretty good estimate. As we can see, we're within 1,000th of it on the left and on the right. So the equation then, we know it would be y equals mx plus b. So y equals 6x plus b. We can use the point that is on the curve there, which was 3, 9, and say 9 equals 6 times 3 plus b, which means that 9 equals 18 plus b, b equals negative 9. So the equation of this tangent line, y equals 6x minus 9. Now, we don't use a graphing calculator too much in this course. In fact, I don't let you for your tests and quizzes, but if you grab yourself that calculator and graph y equals x squared, and you graph y equals 6x minus 9, you should see a tangent line that comes and just touches the parabola at that one spot and has a slope of positive 6 and a y-intercept of negative 9, and is actually the tangent line at the point 3, 9.